Let's break down FlashAttention-2, faster attention with better parallelism and work partitioning, from Tri-Dow at Princeton and Stanford. Same math, 7 times faster. You already know what attention does. Here's the part nobody mentions. The slow bit isn't the math. This is the score matrix. Every token against every other token, and standard attention builds the whole thing, writes it to memory, reads it back, writes it again. The arithmetic is trivial. The shuttling is everything. FlashAttention-2 computes the exact same numbers, not an approximation, the same numbers, and never builds the grid at all. 7 times faster than the attention most people were running, and the reason long context stopped being a luxury. A GPU isn't one pool of memory. It's a hierarchy, and the gap is brutal. At the bottom, HBM, 80 gigabytes on an A100, about 2 terabytes a second. Sounds quick. Up top, SRAM, on chip, right beside the compute units, 19 terabytes a second, but you get roughly 200 kilobytes of it per multiprocessor. So the only question that matters is what lives up there. Standard attention's answer is nothing. It parks the n-by-n grid in HBM and drags it across the bus 3 separate times, which makes attention memory-bound, and that's the whole insight. Operations come in 2 flavors. Compute-bound, a fat matrix multiply, so much arithmetic the memory traffic vanishes into the noise. Memory-bound, barely any math per byte, so you sit there waiting on the bus. Softmax, masking, dropout, every element-wise pass over that grid is deeply memory-bound. So cutting flops, the optimization everyone reaches for, optimizes the thing that wasn't costing you anything. Count bytes moved, not operations performed. So why not skip the grid and go straight to the output? Because softmax is nosy. To normalize one score, you need the maximum over the entire row for stability and the sum of every exponential in it. Both are reductions across all n columns. You can't finish one weight until you've seen all of them. Here's the fix. Take the row in chunks and carry 2 running numbers, the largest score so far and the running sum. When a chunk arrives with a bigger maximum, you rescale the old sum by 1 exponential factor, then add. Exact at every step. Nothing approximated. Now put it on silicon. Cut the queries into row blocks, the keys and values into column blocks, and the grid becomes a checkerboard of tiles small enough to fit in SRAM. Load one tile, compute its scores on chip, fold them into that query block's running statistics. And here's the move. Keep the running output vector 2 and rescale it by the same correction factor whenever a bigger score turns up. One fused kernel, load, compute, write. The n-by-n matrix is never allocated. Quadratic memory becomes linear, and the answer is bit for bit identical. The whole recipe in one sentence. Training needs gradients, and the textbook backward pass wants exactly the matrices we refuse to store. Awkward. The answer is recomputation. The forward pass kept the output and one number per row, the log sum exp, and that's enough to rebuild any tile from scratch, in fast memory, on demand. It looks like checkpointing, trade compute for memory. But attention is memory-bound, so recomputing a tile in SRAM beats fetching one from HBM. You save the memory, and you get faster. If winning by counting bytes instead of flops is your idea of a good time, like, subscribe, and send this to the friend still optimizing the wrong number. Because version 2 gets properly petty. Here's the thing though, FlashAttention was fast and still only hit 25 to 40% of what the chip can do, while a plain matrix multiply gets 80 or 90. Version 2 hunts that gap. First target, non-matmul flops. An A100 does 312 teraflops of matmul on its tensor cores, but only 19.5 of ordinary math. So each non-matmul operation costs 16 times more. So, pull the division out of the inner loop, accumulate the output unscaled, divide once at the end, and store one log sum exp instead of 2 statistics. Identical output, far fewer expensive instructions. Second target, keeping the GPU busy. Version 1 gave each attention head its own thread block. Fine when batch times heads clears 108, the A100's multiprocessor count. But long context means small batches, and half the chip goes idle. So version 2 parallelizes over sequence length too. Flip the loops so queries sit outside, and every block of rows becomes an independent worker that talks to nobody. Inside a block, version 1 split the keys across warps, forcing them to swap partials through shared memory. Version 2 splits the queries instead. Each warp owns its rows end to end. Added up, about 2 times faster than FlashAttention across the board, 1.7 to 3, depending on head dimension and masking, and up to 10 times a standard PyTorch implementation. 230 teraflops on an A100, 73% of theoretical peak. That's matrix multiply territory for something with a softmax in the middle of it. End-to-end, GPT models train at 72% model flops utilization. Translated, 16,000 token context for the price of 8. For the record. So, the recipe. Attention is memory-bound. Count bytes, not flops. Never materialize the n-by-n grid. Stream the softmax with a running max and a running sum, so it stays exact. Tile into SRAM and fuse it into one kernel. Recompute in the backward pass instead of storing. Then version 2. Spend your cycles on matmls. Split the work across sequence length. Give every warp its own rows. Same attention. Several times the speed. One line. Attention was never compute-bound. Count trips to memory instead of flops. Keep the whole computation on chip, and the exact same math runs several times faster, which is what made long context affordable. Which leaves an uncomfortable question. FlashAttention-2 didn't change the math by a single symbol. It just moved the numbers to a better neighborhood. So how much of what we call a better algorithm is really just better memory? That's my read. Tell me yours. Until next time.